7.5 newtons, okay, which is approximately, it's about 90,000 pounds of thrust. For comparison, the Saturn V rocket, which took our astronauts to the moon at liftoff, had a thrust of about, I think it was 7.5 million pounds of thrust. So, quite a bit more than this toy rocket that I've shown you here.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Recall that Newton defined this quantity of motion, which we now today call momentum, we denote it by a P, as the mass times the velocity. Okay, you guys remember that?
Yeah, I think so.
So the whole idea is that it's this quantity of motion, right? So if you've got two objects that are moving with equal velocity, and one of them is heavier than the other, right, then you can imagine it has a larger quantity of motion, right? And so that would be reflected by its larger mass. Whereas if we have two bodies of nearly the same mass, but say the lighter one is traveling much, much faster, then its quantity of motion would be larger, despite having a slightly smaller mass. You may also recall that we said that Newton's second law can be stated as the net force is equal to delta P over delta T. This is slightly different than our F equals ma version of it, right?
Yes.
We'll talk about this a little bit more later when we talk about relativity in not so far off lecture. But the delta P delta T, right, it's the change in momentum versus the change in time.
Yes.
What does delta P mean? Well, delta P means final mass times the final velocity minus the initial mass times the initial velocity. Let's assume that the mass is the same before and after. So the delta M, if you will, is 0.
Right.
If that's the case, if this is just equal to M times Vf minus Vi, then delta P can be written as M times delta V. If the mass was not the same before and after,
Yeah.
what might that correspond to? Imagine you're standing in a boat on the water, and you've got some bricks in the boat with you, and you start chucking the bricks out the back of the boat.
Boat's going to start moving.
Boat's going to start moving, that's right. But the force which has propelled the boat forward,
You're pushing on the brick pushing back on you.
yeah.
Pushing on the boat.
But the net force that you'll have exerted on it will be the fact that the mass of the boat is decreasing.
Okay.
Okay? If you consider just the boat and yourself and the bricks inside the boat as one piece of the system, and you ignore the bricks that are flying out the back, right?
Yeah.
So the mass is decreasing. So you can think of this as a form of propulsion. This is how rockets work. And so I don't know if we'll actually get to use the rocket equation in any great detail, because again, this is a non-calculus based course. And so without calculus, it's a little difficult to derive and use the rocket equation. But we might use computers to do that. Delta P can be written as the mass times delta V. So now I want you to consider a reaction force pair. Okay? So here we've got particle 1, here we have particle 2. And this I'm going to call F of 2 on 1. This is the force of 2 on 1, which will be equal and opposite to the force of 1 acting on 2. Now let's assume that these were, interacting and touching at some point, okay?
Okay.
I just wanted to separate them so you could see that there were two bodies there. So Newton's third law tells us that F(1,2) will be equal to minus F(2,1).
Yeah.
They're equal and opposite forces. One is acting, this one is the force of 1 acting on 2, you see?
Yes.
And this F(2,1) is the force of 2, this body acting on 1. Okay, so don't get confused about what that means. We could write that F(1,2) delta P over delta T, which as I've written up here, this is M well, I need to put in what this is the force of 1 acting on 2. So this is a 1, 2, I guess we would say. No, we don't need that there, just a 1. So it's mass of, oh wait, force of 1 acting on 2. Okay, so this will be on 2. It's the mass of 2 times delta V of 2 over delta T. And then F21, this is going to be equal to, I guess we call it delta P1 over delta T, which is the mass of 1 times delta V1 over delta T. And then we can use this equality right here from Newton's third law, set these two pieces equal to each other. This gives me that M2 delta V2 over delta T is equal to minus M1 delta V1 over delta T. We can eliminate the delta T's entirely because they are the same, right? This is the same time interval. So I'll just do that right there. I'll move this onto this side so that we get M2 delta V2 plus M1 delta V1 equals 0. Well, what is delta V2? This will be M2 times V2 final minus V2 initial plus M1 times V1 final minus V1 initial. All right, it's an I. And that's equal to 0. Distributing the masses and collecting the final times on one side, and I'll move the initial times to the other side, we finally arrive at the conservation of linear momentum, which says that M2 V2 final plus M1 V1 final is equal to M2 V2 initial plus M2 V2, M1 V1 initial. But another way to write that, right, remember the definition of momentum is mass times velocity. This just gives us that P2 final plus P1 final is equal to P2 initial plus P1 initial. And this is the conservation of linear momentum.
Okay.
It says that and this is for what we call a closed system. So a closed system would consist of these reaction force pairs. Now, it doesn't just apply to two particles that interact with each other. This could be for any number of particles interacting with each other.
Mm-hmm.
This could be an Earth-Moon system,
Okay.
which obviously has lots of particles in it.
Yeah.
So it's not just two particles interacting with each other. It can be any number of particles interacting with each other. You know, some of the kind of problems that we'll work out in the future, you can imagine an object which is whole exploding into several pieces.
Yeah.
So those several pieces would be, you know, the different particles, all of which interacted with each other. In the next lecture, we'll work some simple conservation of momentum problems. It turns out to be a simplification in problem solving if you can apply conservation of linear momentum. So if you know what the initial momentums of momenta of some particles are, and then you know something about the interaction, then you can figure out what the final state of the motion is as well. And so we'll talk about that in the next lecture. This, however, is probably how Isaac Newton came up with his third law, by, you know, bumping objects into each other, finding Newton's third law this way. So he probably started by observing that momentum seems to be something that's conserved in the system,
Okay.
and then gleaning from that the third law. The origins of these conservation principles. This is the first conservation principle that we've encountered. The next one that we'll see relatively soon will be conservation of energy, but we haven't talked about energy yet. These come from certain symmetries
Okay.
of the system, and it turns out that for momentum it comes from the translational symmetry. The fact that this experiment comes out the same regardless of whether I translate my rulers over, you know, 10 meters or not. Does that make sense?
Yes.
So if I do an experiment, right, and say I'm on a football field, and so the football field is my big ruler, right? And I do the experiment at, say, the end zone of one side of the field,
Yeah.
and I translate it to the 50-yard line and do the experiment there, the results are the same. You see?
Yeah.
This is called translational symmetry. And this translational symmetry ultimately is what results in this conservation of momentum, though it would be very difficult to demonstrate that with the limited mathematical tools that we have at our disposal at this time. I will tell you it utilizes some principles and techniques that we talked about when we talked about the principle of least time, which derives from the principle of least action, which we have not talked about, and using that you can show this conservation principle. But conserved quantities turn out to be very important, right? You can also think of them as the constants of the motion. These are the constants of the motion. I think that's all I wanted to say about that. So we'll continue on and see some examples in the next lecture of conservation of linear momentum. You should at least be able to see how it works and how you can use it in problem solving. Okay, so we're going to talk about inelastic collisions as opposed to an elastic collision. An elastic collision is where you would bounce off, like a couple of rubber balls bouncing into each other. An inelastic collision is where the things come together and they stick, and they don't separate. Okay, and as an example of that, consider a bullet fired into a block of wood. So initially, the block of wood is at rest, the bullet is in motion, and afterwards, the bullet is embedded inside the block of wood, and the two move together. You see?
Yes.
So let's set up our conditions. What is our, well, let's write down what these numbers are going to be. Our mass will be equal to 10 grams, which is going to be 0.01 kilograms. And the velocity, the initial velocity will be 1,000 meters per second, which is a very fast bullet.
Okay.
So what conservation of momentum is what we're going to use here.
Okay.
Because conservation of momentum tells us that, I'll put it up here, that P final will be equal to P initial. Okay, that's the final momentum of the system, of the bullet and the wooden block, will be equal to the initial momentum of the bullet and the wooden block. So initially, what do we have? I guess I need a mass for the wooden block here as well. So M2, we will set to be 490 grams, or 0.49 kilograms. Well, so initially, P initial will equal, say, P1 initial plus P2 initial, where that's the momentum of the bullet plus the momentum of the wooden block. Well, the momentum of the bullet is the mass of the bullet, M1, times V1, the velocity of the bullet. And the momentum of body 2 is the M2, mass M2, times the velocity V2. But I said that the block is not moving initially, so this will be 0. V2 will be 0, so this term will go to 0. And so our initial momentum, we'll find, is just equal to M1 times V1, which is 0.01 kilograms times 1,000 meters per second. And that will be equal to, I think, 10 kilograms meters per second. So that's our initial momentum. There are no units of momentum, like official unit, like newtons or something like that. You know, it's not Galileos or something. So standard units, though, will be kilograms and meters per second.
Okay.
Afterwards, what do we have? Well, P final is going to be, it's the same as before, it'll be P1 final plus P2 final. But since these both have the, this will be M1 times V, they'll have the same, or V sub S. They both have the same velocity because they're moving together, right? So that's M1 times V sub S plus M2 times V sub S, which is just equal to M1 plus M2 times V sub S. And M1 plus M2, that's 490 grams plus 10 grams is 500 grams. That will be 0.5 kilograms times V sub S.
All right.
We don't know what V sub S is, that's what we want to find out. That's what, with the question mark there. So we're going to solve for that. because that's the unknown that we have, okay? We can solve that using conservation of linear momentum. We set the final momentum, which we have here, 0.5 kg times v sub s equals the initial momentum, which was 10 kilograms meters per second. 10 kilograms meters per second. We can multiply both sides by 2, and that will give me v sub s equals 20 meters per second. So it's a pretty quick moving block.
Okay.
So all I did was just solve for v sub s by dividing out 0.5 kilograms from both sides, right? And that left me with 20 meters per second is the velocity of the block and the bullet moving together.
Okay.
And that is an example of an inelastic collision. Does that make sense? And and we solved it using, conservation of momentum.
All right.
It's probably worthwhile for you to think about how would I have solved this if I did not know about conservation of momentum.
Okay.
You probably would have had to make some assumptions about the force that the bullet applied to the block, right? And we don't have any details regarding that. We didn't even need them.
All right.
Now, this is, of course, assuming that there was nothing lost. This is an idealistic number. In reality, the speed would be a little less than this because it would take away some of the energy that the bullet had, and energy some we haven't talked about yet, but some of the energy the bullet had would have been lost to the heat, the deformation of the wooden block, because it takes energy to do that, and some heat that would be generated, right, as it slid into the wooden block.
Okay.
And so that energy would reduce the velocity of the system that resulted afterwards. But again, we haven't got to energy yet, and once we do, we will use it to deal with different collision problems. Maybe we'll do some, more complicated collision problems, but I don't know that we will. But we'll certainly do elastic collision problems, which will need energy. We'll have to talk about energy first before we can do that. All right, well, I think that's it then. All right, today's lecture is on impulse. Impulse is another kind of quantity of motion which is sometimes useful. It's defined as the force times time. Here's an example of impulse. Imagine a car traveling with some initial velocity called v sub I and driving into a tall grassy field, right, and allowing the grass, right, to slow the car down until it comes to a complete stop sometime later.
Yeah.
So its final velocity is 0. Now imagine starting out at the same initial velocity in the same car and using a brick wall to slow yourself down, right? What's the difference in these two? Well, recall that force can also be written as delta P over delta T. And so if we define force times the time, or force times delta T, as the impulse, then you can see that the impulse is also equal to the change in momentum. So in both cases here, the momentum went from an initial state, where the car had some mass m and some initial velocity vi, and in the end it still had mass m, but its velocity was 0.
Yeah.
So the change in momentum is the same in both cases here, right? Delta P1 is equal to delta P in 2. Well, this is Roman numeral 2, Roman numeral 1.
Yeah.
So the change in momentum in both cases is the same. So what's the difference in these two pictures? Well, which one would you rather be in?
The grass.
Car 1 or the car in case 2?
Or case 1.
Car in case 1, right? Coming to a nice gentle roll. So what's the difference here? Well, in this case, the force is rather small, but the time period, delta T, is rather large. So over here, even though the impulse is the same amount, it's a small force times a big delta T, right? Because it took a long time for this car to come to a stop, right? Whereas in this case here, we have a huge force and a little tiny delta T. You see? So in one case, it's the force which is big, and in the other case, it's the delta T that's big.
Okay.
So that's the difference between these two cases. Another way to think about impulse too is that if you really want to change the momentum of something, then you apply a force for a longer period of time.
Okay.
So if I apply a force F, right, say it's just, 1 Newton is about the force that you push with on your finger like this, right? It's about a Newton. If I do that for 1 second versus 100 seconds,
Yeah.
at 100 seconds I can accelerate something quite quickly.
Yes.
I can bring it up to a very high velocity if I apply force of 1 Newton for 100 seconds. Whereas for just 1 second, you know, it's not going to be at a very high velocity in the end, right? So I don't change its momentum by much if I'm just doing it for 1 second. So, interestingly, rockets, or model rockets specifically, the engines for model rockets are designated by their impulse. And so if you get a rocket motor that says an A on it, A corresponds to 2.5 Newton seconds of impulse.
Okay.
Remember, newtons are the unit of force, and seconds are the unit of time, and so impulse, force times time, will have units of Newton seconds.
Okay.
Whereas a B motor will have 5 Newton seconds of impulse. A C motor will have 10 Newton seconds of impulse.
Okay.
Now there are some more numbers that usually are given to you for a rocket motor. You might have like a B10 or a B5, and what that's going to tell you in the end is ultimately what the time, the burn time is, how long the motor is going to burn. And so you'd use, if it said B10 for example, you say, okay, well I know that B is a 5 Newton second motor, right? So B10 must be, the 10 means 10 newtons, okay? And since I only have 5 Newton seconds, that means that the burn time is going to be 1/2 second, you see?
Yeah.
So you figure out the burn time for that. But here I'm going to give you some burn times, and we'll just use these kind of stock numbers here. So let's consider how we can figure out what the final, or the maximum speed of the rocket is. So we know that delta P, which is going to be equal to the impulse, that'll be equal to the final mass times the final velocity minus the initial mass times the initial velocity.
Okay.
Now the initial mass will actually be bigger than the final mass, because the final mass will reflect the fact that the rocket has burned some of its mass in propellant.
Okay.
But we're not going to worry about the details of that. The initial velocity, however, is almost always going to be 0, because we usually launch these things from some launch tower and they'll be sitting still on the ground. So since the initial velocity is 0, we don't even really need that at all.
Okay.
And so this is going to tell us that delta P is going to be equal to the final mass times the final velocity. And from this I can solve for V sub F, and that would be delta P over the mass.
All right.
So we need some numbers for this now. Let's assume that our final mass, so that's the mass of the rocket after it's already burnt all of its propellant. And you could get this by, if you already had a rocket motor that you've already used,
Yeah.
right? Stick it in the rocket, weigh the rocket. That'll be its final mass.
Okay.
But let's assume that m sub f, it's right over here, m sub f is equal to 50 grams. Not far off for a model rocket. And let's consider what's the final velocity if we launch with an A motor and maybe also a B motor. See what the difference is going to be. Well, actually, let's do a B and a C motor. I think that would be, for starters, it would be easier. So if we launch it on a B motor, also I'm going to assume that the burn time, TB, is going to be equal to 1 second. I'll write that SEC so it's clear it's a unit. I think that's all the inputs that I need. So now this final velocity is going to be also going to be the maximum velocity of the rocket, right? It's never going to be going faster than it is at the moment its motor burns out.
Okay.
So what happens is it's going to accelerate up from the rocket thrust, right? Getting faster and faster and faster. And then the rocket motor turns off, burns out. So we call it burnout time, right? And now it's coasting, right? So it's got its maximum velocity. It's still going up, right? But gravity, of course, is accelerating downward, right? And it's going to cause it to slow down. So its velocity will decrease until it gets a velocity of 0 at its apex, and then it'll fall back down to 0.
Okay.
So we can also call this V final. We can see that this is the V max. That's the maximum velocity of the rocket. So for a B motor, this V max is going to be equal to, well, delta P, that's just the impulse, right?
Yeah.
And an A motor, or excuse me, a B motor has an impulse of 5 Newton seconds. So that is 5 Newton seconds divided by the mass, final mass, which is 50 grams. So that's 0.05 kilograms. And that is going to give us 100 meters per second.
Okay.
That's its final velocity, 100 meters per second. That's about 230 miles per hour. That's pretty quick, huh?
Yes.
If we launched on a C motor instead, then Vmax would be equal to 10 Newton seconds, because the impulse of a C motor is 10 Newton seconds. I think I mentioned that these always double, right? So a D motor would be 20 Newton seconds. An E motor would be 40 Newton seconds, so on and so forth, right? The biggest motor I've ever launched a rocket on, I think, was a J motor, which is right around 1,000 Newton seconds.
Okay.
So, but anyways. So Vmax for this, still, I'm going to assume that the burnout mass is the same. In reality, they're going to be a little bit different, right? Because the motor itself is a little bit bigger. So if it's the same rocket, and I use, say, a B and then a C motor, the burnout mass will be just a little bit different, but we'll assume it's the same. And so this will give me, of course, 200 meters per second.
All right.
So 460 miles per hour. Pretty fast, right?
Yes.
Now, of course, we're completely neglecting air resistance here.
Yeah.
And I'm not going to include air resistance in these calculations. Let me just say it will at least cut these numbers in half.
Okay.
Because the air resistance that you feel is proportional to the square of the velocity. It's also proportional to the cross-sectional area of the rocket, the density, and then your rocket shape will determine a drag coefficient you'll have to use in there as well. But anyways, it's going to reduce these velocities and also altitudes quite a bit.
Okay.
So what we're going to do now, we've got these maximum velocities, right? So that, of course, is, during the boost phase, right? And I'm going to kind of draw this up at an angled flight, right? This is the boost phase, right? And so here at this point, right, we're at Vmax. I should draw that a little bit bigger. So right here is burnout, right? There's my little rocket. And that will be Vmax.
Okay.
Now what's it going to do? It's going to coast for a bit, right? Until it reaches its, its apogee, right? Its maximum altitude. So how do we figure out how far it's going to coast? Well, first we have to figure out how far has it traveled so far. Well, at the end of this, at burnout, it's traveling at this maximum velocity. But it wasn't traveling that fast the whole way, so I can't use that times the burn time. Right? I know the rocket fired for 1 second. So this is how far does the rocket go after 1 second. Right? So what is the quantity of motion that we use to figure out how far something travels? You want to remember from kinematics? Right? What is the right thing to use to figure out how far something travels?
We need several things, though.
Well, I know the time. It's going to do something it's going to travel for 1 second, because that's the burn time of the rocket, right?
The speed and the angle is...
Well, you can't use the max speed, right? Because it wasn't traveling at this speed the whole time. If I use the max speed times 1 second and said that it's traveled, 100 meters, that would be wrong. Because when it started out, it was going 0.
Okay.
But what I can use is I can use the average velocity. Right, starting out at 0, it ended at 100 meters per second, right? So the average velocity, which we'll call V average, like this, okay? And I'll put D here for a B motor, will be equal to 0 plus 100 meters per second divided by 2. So that's 50 meters per second. That's its average velocity. The average velocity for the C motor, on the other hand, would be 0 plus 200 divided by 2, which is equal to 100 meters per second. So what that tells us is that the distance that this traveled, right? Now I'm going to assume that it's actually traveling straight up in the air. But the distance that it traveled up in this direction, we'll call this D sub B for the burn distance, right? The distance it traveled to burn out, maybe a BO, like that. This is going to be equal to the average velocity times the burn time, D sub B. So in this case, D sub BO will be equal to 50 times 1 second, right, which is equal to 50 meters. And for the C motor, right, D sub BO will be equal to 100 times 1, which is 100 meters. Okay? So that's the distance that it traveled during the burn time while the engine is firing.
Okay.
And I use the average velocity to get that distance.
Okay.
Now I want to figure out how far it's going to coast. And if you go back to lecture 6, in lecture 6 I derive an equation, right? This last part of it here, right? This last distance, which we'll call delta x. We can get this from the following relationship. 2 times gravity times delta x is equal to v final squared minus v initial squared. This is a kinematic equation that I derived in lecture 6. And so you can go back and watch that and see how I did that. Alternatively, you can use the old way of doing it. You can say, well, I know its initial velocity is v max, and its final velocity is 0.
All right.
And I can ask, well, so the time that it takes, you know, when is it 0? Well, whenever what's the time period of this travel? Well, I figure out how long it takes before it gets to a velocity of 0 using the acceleration of gravity, right?
Yeah.
And then I use that to figure out how far it's traveled in that time period. But this combines both of those calculations into it, and so we can just use this equation here. We solve for delta x, right? So in this case, our v initial, right, will be the maximum velocity.
Yeah.
So we'll get that delta x is equal to, the final velocity will be 0, because that's at apogee, right?
Yeah.
And so we'll have a negative v max squared divided by 2 times g, but remember that g is negative because this is accelerating in the downward direction, so that'll kind of cancel the sign of this guy out. And the acceleration due to gravity we'll use in meters per second, and we'll say that it's about 10 meters per second.
All right.
And 2 times 10 is 20, so we'll do 20 meters per second squared.
All right.
So if I now plug in what delta x for, say, a B motor is, that's going to give me V max, which I'll use this here, that's 100 squared divided by 20, and that's going to turn out to be, that's 10,000 divided by 20. I believe it comes out to be 500 meters. And for the C motor, this distance is not 100 meters per second squared, but 200 meters per second squared, right? 200 squared over 20, and this will be 2,000 meters. Okay?
Okay.
And so the question now is, what's the total height, right? What's its maximum altitude, or the altitude of apogee, right? Well, you just add these numbers to the distance they travel during the boost phase.
Yeah.
So the B motor, we'll say altitude of the B motor, right, will be the d sub b o plus, well, let's say altitude is equal to the d, the burnout distance, plus delta x, the coasting distance. And so for a B motor, we would get 50 meters plus 500 meters, which gives us 550 meters. And for the C motor, it's 100 meters plus 2,000 meters, which is 2,100 meters. That's terrible. Meters. Which is about 1 1/3 mile up.
Okay.
Now, again, reality, you know, half that, you know, at best, because of drag from air resistance, because especially when you're going fast, right?
Yeah.
And these rockets can go really, really fast. If you put these rockets on, maybe an M motor, for example, they're going so fast that if you were to paint the nose cone, for example, that would all melt off. If you were to use a plastic nose cone, it would melt. So you have to use something like, you could use metal, like titanium. The body, you'd want to use carbon fiber, because the friction, the heat from the friction is going to be so high that it would melt it if it was anything other than that. Or you can make it out of aluminum, of course. Okay?
Okay.
So, impulse. It tells us what the change in the momentum is going to be.
Okay.
And we've used it here to show how high a model rocket will go and considered for a B motor and a C motor. All right, so before we move on, I wanted to go over one more interesting application of the conservation of linear momentum, and that is to derive the rocket equation. Now, traditionally, the rocket equation requires calculus to solve, so what we're going to do is a slightly different version of it. We're going to develop a set of recursive relations, which we'll be able to use to get some numbers for what the velocity of this rocket is after some time t. Okay? And here's how we're going to do it. So we're going to have this kind of before and after picture. So I'm going to let this be t equals 0, and I'll let this be t equals 1 second. So initially, the rocket has not fired anything. It's just sitting, we'll say its velocity is 0. We'll make that relative to, say, the Earth, but I'm not going to put gravity in here. We'll assume that it's already very far away, but we're tracking it from Earth, okay? So in that case, the velocity v will be the speed of the rocket once it gets going. But initially, its velocity is 0, right? So here we have that v is equal to 0. Also, I'm going to write this as v sub 0, meaning v at time 0. This will be v at time 1. And so our objective here is to figure out how can we calculate v at time 1.
Okay.
So before, nothing has happened, but afterwards, we have fired our rockets. This has resulted in a change in mass of our rocket ship. Typically, rockets are about 80 to 90% fuel by mass.
Okay.
So that would be a 10 to 20% payload weight.
Okay.
So as we fire the rocket, it ejects the mass out the back, right? This is usually through a chemical process, right? There's an explosion that takes place in a chamber, and those fast-moving gas particles, right, from the ignition are directed out the back of the rocket. It's a little bit like sitting in a boat and throwing bricks out the back end. You'll observe that when you do, A, the boat gets lighter, right?
Yeah.
And B, the boat starts to move. It obtains some velocity.
Okay.
Now, we're going to assume that because of the combustion process, the uniqueness of the combustion process, that the speed at which the gas particles are being ejected out the back, which we'll call exhaust, is constant. We'll call that v sub ex.
Okay.
But now relative to Earth, the speed of the exhaust particles will actually be v sub 1 minus v ex.
Okay.
Because if the rocket is moving, then the exhaust particles will be moving as well.
Mhm.
And so we'll have to take the difference. It's just a relative frame of reference. We talked a little bit about frames of reference before. You know, if you're on a train car and you throw a ball at 5 meters per second, on the train car, the speed of it is 5 meters per second. But to someone on the ground, they're going to see it equal to 5 meters per second plus the speed of the train.
Okay. Yeah.
If I'm moving away from the person standing on the side of the tracks and I throw the ball backwards, so I throw it at minus 5 meters per second, right? So then you'll have to take the speed of the train minus the speed of the ball that I threw to see its relative velocity. So the speed of the gas particles relative to the Earth is the velocity of the rocket minus the velocity of the exhaust particles. So now what we can do is we can set up a conservation of momentum situation. Before, so P before, will just be equal to m0. Why did I call it m0? That's the mass of the rocket at time 0.
Okay.
We haven't lost any, we haven't made any, haven't combusted anything yet. So we still have all the fuel plus the payload, right? So this will be the payload plus the fuel
Okay.
times the velocity at time 0, which you might recall is 0. P after is going to be equal to the momentum of the rocket plus the momentum of the exhaust. It's a little bit like a rifle recoil problem, right? If I shoot the rifle, the bullet will shoot out the end of the rifle, right?
Yeah.
But there's a recoil force, right, in the opposite direction.
Okay.
Those forces are equal because they are interaction force pairs, right?
Yeah.
But the speeds aren't equal, right? Gases are coming out at a very high speed. The rocket is not moving at an equal speed, right? So we can calculate what these terms are, though. P of rocket is just going to be m1, because it's after, right? T equals 1, times v1, velocity of the rocket, plus the momentum of the exhaust. Well, that's going to be this term v1 minus v exhaust times this delta m. This delta m is the little bit of mass that I've combusted and shot out the back. So you can see it's represented here as this little piece of mass. It's flying out the back.
Okay.
And it represents the change in the total mass of the rocket ship.
Okay.
And so at this point, we'll need to observe, I'll write note, that m1 is equal to m naught, or m sub 0, minus delta m.
Okay.
Because that's the new mass of the rocket. It's a little bit lighter than it was before. So if I substitute that in for m1, I'll get m naught minus delta m times v1 plus v1 minus v exhaust times delta m.
Okay.
Now I'm going to distribute these two terms and just do a little bit of algebra. So we'll get m naught v1 minus v1 delta m plus v1 delta m minus V exhaust delta M. Now notice that these two terms here are the same, and they cancel, right? And so all I'm left with in P after is M naught V1 minus V exhaust delta M. Conservation of linear momentum says that P before is equal to P after, which says that M naught V naught is equal to M naught V1 minus the exhaust delta M.
Okay.
Now what I want to do is I want to solve for V1. That's the unknown quantity, right? That's the unknown velocity we don't have yet, right? So let's solve for V1. And what we'll find, after dividing out M naught and moving the exhaust velocity over to the other side, we'll have V naught plus V exhaust times delta M over M sub 0.
Okay.
That's for one time step, right? That's going from t equals 0 to t equals 1. We can generalize this for any time step. So I'll say for the nth time step in general, V sub n, the nth time step, is equal to the previous time step, the n minus 1 time step, plus the exhaust velocity times delta M divided by M, the previous mass, M sub n minus 1. So any questions on what we've done so far? It's pretty straightforward, right? We just calculated the momentum before, which was just M naught V naught, right?
Yes.
And then the momentum after, which is the momentum of the rocket plus the momentum of the exhaust.
All right.
Probably the funniest bit of business that we've done here is that we've written the velocity of the exhaust as a relative velocity with reference to an inertial reference frame like the Earth.
Okay.
So we have to subtract the exhaust velocity from whatever velocity the rocket may have at that moment.
Okay. What do you mean by in general?
Oh, well, so here I did it for one time step, right? So what I'm saying now is that we could keep doing this, right? We could then calculate V sub 2, and we find that it was equal to V sub 1 plus V exhaust times delta M over M1. And we could keep going in that fashion, which means that for any time step, right, the velocity will be equal to the previous time step's velocity plus this term right here.
Okay.
Does that make sense?
Yes.
Okay. So now let's put it to practice. Let's actually calculate some stuff with it. So I'm just going to erase these equations here. Maybe I'll write the result up here. That V sub n is equal to V sub n minus 1 plus V exhaust delta M over M of n minus 1. Well, remember, these subscripts tell me what time step I'm on. Okay, so I've discretized the time steps. This would be a very good way to do it if you were going to do it by computer, for example, and simulate this stuff on a computer. You could even put this into a spreadsheet and calculate these velocities. You'd have to do it recursively. You'd have to calculate the first time step, and from that calculate the second velocity, right, in the second time step, so on and so forth. That's what we're going to do here. We're going to make a table. So we'll say T, M, and V. So time T equals 0, the mass, and we'll set some, well, use some parameters here. Let's let the mass be equal to 100 kilograms. Let's let delta M be equal to, I think, 10. That's what I did in my notes. 10 kilograms. Okay, so each time step, it's going to be combusting 10 kilograms of fuel.
Okay.
And, of course, the initial velocity will be 0, right? So V sub 0 will be 0. It's going to be handy to have this term, right? This V sub EX times delta M. That's going to be 100 times 10. Oh, I didn't specify the exhaust velocity. I need to put that in here. The exhaust velocity is going to be equal to 1,000 meters per second.
Okay.
So 1,000 meters per second. So V sub, the exhaust velocity times the change in mass will be 1,000 times 10. That's 10,000, and that'll be kilogram meters per second.
Okay.
Don't worry about the units because we're going to use this in this recursive formula. So initially the mass is 100 kilograms, right?
Yeah.
And the velocity is 0. So that's the 0th time step when we just start out, right? The initial condition. At the first time step, what is the mass going to be? Well, remember, the mass for the nth time step is equal to the mass for the n minus 1 time step minus the delta M, right? Whatever we're subtracting off of it. So each time step we're subtracting from the total mass of the rocket, this delta m, right? So that 10 kilograms. So in the mass at time t equals 1 of the rocket will be 90 kilograms.
Okay.
What's the speed of the rocket? Well, our formula says that it's the previous speed, which is 0, plus this velocity of the exhaust times delta m, which is 10,000, right? Divided by the mass from the previous time step. Well, the mass from the previous time step was 100, right? And so that is going to be equal to 10,000 divided by 100. That's going to be equal to 100 meters per second.
Okay.
In the second time step, the mass will decrease to 80. I'm just subtracting 10 kilograms off each time I take a time step, right? So t equals 2. That's the second time step. Our mass goes down to 80 kilograms. What's our speed going to be this time? Well, it's not 0, right? It's the previous velocity, which was 100 meters per second, plus this 10,000 again, right? That's that velocity, the exhaust velocity times the change in mass, divided by the old mass, which is 90, right? And so this comes out to be approximately, I think it's 211 meters per second. In the third time step, the mass will be 70 kilograms. The velocity will be the 211 meters per second from the previous time step, plus 10,000 divided by 80, which is going to be approximately 336 meters per second. In the fourth time step, we'll have a mass of 60 kilograms, and our new velocity will be 336 meters per second plus 10,000 divided by 70, which is approximately 479 meters per second. Okay? Now I'm just going to keep filling these values in. This will be 50, and this will turn out to be 646 meters per second. In the sixth time step, this will be 40, making this 846 meters per second. In the seventh time step, we'll have a mass of 30, and we'll have a speed of 1,096 meters per second. And in the eighth time step, we'll have a mass of 20, and that'll give us a speed of 1,429 meters per second. And then in the ninth time step, we'll have a mass of 10 kilograms, and our speed will be 1,929 meters per second. Now, I'm going to assume that our rocket ship was a 10% payload rocket, and so we're out of fuel. Okay? All we have is 10 kilograms of payload, right?
Yeah.
Left. Okay? Now, if we plot these values, what does it look like? Well, we're going to go up to roughly about 2,000 up here, right? So 2,000 meters per second for our velocity, which means that about halfway we'll be at 1,000 meters per second. As far as time goes, we'll say if this is, roughly 10 seconds, we'll make this 5 seconds. So we've got some point. 9 seconds, right? So about here, we're almost 2,000 meters per second in our velocity. So we'll put that here. Okay? For our, at 5 seconds, where were we? 646, so this would be 500, so maybe somewhere around here, right? And we can at 0, of course, we're at 0. And if I just kind of interpolate these points, it's going to look something like this. So I'll just move that, fit my graph. So this is the function that we get for our velocity.
Okay.
Okay, so this gives us the velocity of the rocket as a function of time. You can see it's getting faster and faster and faster and faster, right?
Yeah.
Up to burnout, at which point it's just going to continue traveling on at that constant velocity. Because we're assuming it's in space or something, right? So now that we've seen an example of this calculated, and of course you could write a computer simulation that could do this. You could put in more realistic parameters. You could take far more time steps.
Okay.
You could even add in the effects of gravity and stuff like that. Now I want to look at this rocket equation just a little bit more. If I take this, notice that delta V, right, is equal to V sub n minus V sub n minus 1.
Yeah.
So if I just subtract V sub n minus 1 from both sides, I'll get that this is delta V equals exhaust velocity times delta m over m sub n minus 1, which I'm just going to call m for now, okay? That's just the current mass of the rocket at some time t, right? Like I could put in as a function of t if I wanted to. If I divide both sides by delta t, I'll get delta v over delta t equals exhaust velocity times delta m over delta t times 1 over the mass as a function of time. Yes?
Yes.
Multiply both sides by the mass, and I'll get the mass as a function of time. time. What is delta V, delta t, by the way? What is that quantity called? The change in velocity divided by duration is?
Acceleration.
Acceleration. All right, so this is my acceleration. I'm just going to write this as m, right, so that we're not confused. This will be equal then to v e sub x delta m over delta t. Where delta m delta t, that's your fuel burn rate, right? How much mass per unit time am I burning fuel?
Yes.
If I multiply that times the exhaust velocity, it turns this into the thrust, which is a force.
Okay.
Mass times acceleration, that's a force. So we can like see this as like, well, this is Newton's law now, right? Saying that the sum of the forces, in which case we only had one, the thrust, is equal to the mass times the acceleration.
Yeah.
And of course, we're allowing the mass to be a function of time as well, as is the acceleration. So it's a little more complicated. I'm not going to get into the details of that. But this is the thrust. So let's do a quick calculation for some thrust. Before, what was our example? No, I'm going to do a different example. Let's say we have a burn rate, fuel burn rate, delta m over delta t, is equal to 200 kilograms per second. Right, that's a lot of mass. Every second you're burning 200 kilograms of fuel. How much thrust are you going to produce? That's what I want to figure out. Well, kind of a typical exhaust velocity might be 2 kilometers per second. That's 2,000 meters per second. So I can calculate the thrust. We'll call it F. Thrust will be equal to 2,000 meters per second times this 200 kilograms per second. That is going to give me 4 times 10 to the 5 newtons. Okay, which is approximately, it's about 90,000 pounds of thrust. For comparison, the Saturn V rocket, which took our astronauts to the moon at liftoff, had a thrust of about, I think it was 7.5 million pounds of thrust. So quite a bit more than this toy rocket that I've shown you here. Right, the last thing I want to mention is that had we had calculus at our disposal, we would have done things differently. We wouldn't have generated this recursion relation, or recursive relation, to calculate the velocity for the rocket. Instead, we would have set up what's called a differential equation, right? We would have used calculus to solve this thing, and we would have found that the rocket equation says the final velocity is equal to the initial velocity plus the exhaust velocity times the natural logarithm of the initial mass divided by the final mass. So here, this would be just to calculate what is the final velocity of the rocket at burnout.
Okay.
So it's going to be equal to the initial velocity plus the exhaust velocity times the natural logarithm of the ratio of the initial mass to the final mass. Okay. So using our 90,000 pound thrust example from before, if we said that the initial mass of the rocket was 20,000 kilograms, and of course that its initial velocity was 0, and let's assume that we have a 20% payload, then the final velocity of the rocket will be equal to, and remember in our previous example we had an exhaust velocity of 2 kilometers per second. So I'll have the 2 kilometers per second. I didn't put in the 0 initial velocity, but it's there. Times the natural logarithm of the initial mass, which was 20,000 kilograms, over the final mass, which is going to be 4,000 kilograms. And that will be equal to 2 times the natural logarithm of 5, which is approximately 3.77 kilometers per second.
Okay.
So pretty quick, right? If you're moving a few kilometers, that's almost 4 kilometers a second. Can you imagine going at like roughly 2 miles per second? That's a pretty quick clip, okay? Might leave it as a homework problem to figure out the Saturn V, if you assume a constant thrust, which of course wouldn't be the case, what its final speed would be. That might be a problem I give you for the homework.
Okay.
Okay, that's all I wanted to say about the rocket equation, but it's a neat example of the application of conservation of linear momentum, right, to solve the problem. And if we did the calculus approach to it, we would have also used conservation of linear momentum. We'd have just done it a little bit differently. But we get essentially the same result. And the graph I showed you, you will get the same thing, provided you take a small enough time step. Our solution will approximate the true analytical solution that you would have gotten from calculus.
Okay.
All right, that's it.